The main focus of research activity in this lab is mechanical testing. We tend to test materials under different loading conditions to understand how damage starts to happen in metallic and composite materials, and eventually how they break under different loading conditions. So because of the nature of our mechanical testing, the applications are quite different. The application can be for aerospace industry, it can be for offshore oil and gas industry, it can be for renewable energy industry. Eventually, in any industry, we do have materials which have been designed for a certain number of years of operation. And here in this lab, we are interested to test these materials by replicating the service loading conditions to understand what is the realistic lifetime of a material designed for a particular purpose. Using these mechanical testing machines, we can pull samples in tension, or we can just pull them in compression, depending on the loading conditions that a given component or structure is experiencing during the lifetime. And we tend to observe the initiation and propagation of cracks in the engineering materials which are being used in industry. So by monitoring the behavior of crack initiation and propagation, we help industry to have a more realistic assessment of the lifetime of their engineering components and structures. We do have 6 mechanical testing machines in the Structural Integrity Lab. The load carrying capacity of these machines ranges from 10 tons to 250 tons. So on the smaller machines, we tend to scale down the samples, and by doing some fundamental research, we understand the crack initiation, propagation, and damage evolution, especially in welded joints which are used in offshore wind turbine foundations. And then by scaling up the size of the samples, we try to understand the size effects on the design and life assessment of engineering components and structures. So a part of our testing in the Structural Integrity Lab at Cranfield is to simulate the environmental damage that engineering components and structures experience during the lifespan. A part of our research is, for example, called corrosion fatigue test. In those tests, we soak the sample in simulated seawater to replicate the actual environmental condition that offshore wind turbine foundations experience during the service. And at the same time, we apply cyclic loading condition, which replicates the loading condition that offshore wind turbines experience due to the exertion of the wind loads, the wave loads, as well as the current loads. So the loading conditions and the environments that we choose for our experiments are effectively replicating the realistic loading conditions that engineering components and structures experience during the lifetime. We do have advanced mechanical engineering MSc course, as well as the renewable energy engineering MSc course, which are directly linked to the activities that we've got in the Structural Integrity Lab. We do have a module which is named Structural Integrity. As a part of that module, we do have lab demonstrations, so MSc students get to come to this lab and observe some of the typical testing that we do here. And during the group project and individual thesis project, some of the students will have an opportunity to work alongside postgraduate researchers, PhDs and postdocs in this lab, working on mechanical and numerical analysis of structures. One of the recent MSc group projects that was conducted in the Structural Integrity Lab was focused on the design and integrity assessment of flange bolted connections which are used in offshore wind industry. The background of this research came from offshore wind companies. They do experience lots of problems with self-loosening of the bolts which connect the foundation of offshore wind turbines to the rest of the structure. And this self-loosening imposes a lot of inspection for retightening of the knots which are used in these offshore wind turbines. Therefore, this MSc project was defined to better understand the reasons for self-loosening mechanism in these bolted connections in the first step, and in the second step, trying to provide a more reliable tightening techniques to reduce the number of inspection frequencies for the offshore wind sector. The main focus of my research group's activity is for design and life assessment of offshore wind turbine foundations. Here in this lab, we do lots of testing on materials that offshore wind turbine foundations are made of, including the welded sections, which are typically the parts which initiate the cracks and some defects are observed during the operational lifespan of offshore wind turbines. So we test these materials in air and in simulated environmental loading conditions, which is in this case seawater, and we try to understand the actual lifetime of materials which are used in offshore wind turbine structures. So because of the nature of our research, my research group closely collaborates with offshore wind companies. We work a lot with offshore wind designers, operators and consultants, and a lot of our research here at Cranfield is very applied, which means that we tend to understand the problems which industry is facing at the moment, and by doing some underpinning research, we try to find solutions to those problems. Additive manufacturing is one of the recent advanced manufacturing techniques which has been used in research scale at the moment. There are lots of feasibility studies which are being conducted around different research centers across the world. And here at Cranfield, we actively test materials produced using different additive manufacturing techniques, trying to understand the strength and resistance of these 3D printed metallic materials to aggressive loading conditions. And the purpose of our research is trying to build structures which are 3D printed in the future, made of metallic materials for applications in different range of industries, including offshore wind.
My research is about additive manufacturing technique, which is very new at this moment, and we would like to fully characterize a few materials which are made with additive manufacturing technique. And my research is with collaboration with NTNU in Norway. So together we are trying to get a big picture of two types of steel, but they're like kind of unique because they're only used for additive manufacturing purpose at the moment. That's why no one is sure about the behavior of such materials. So one of the tests which we are doing is fatigue crack growth. So you can see that CT specimen is attached to this machine and then it's being pulled with cyclic load condition, and we are looking how quickly the crack propagates through this specimen. And we have this clip gauge here attached, which is estimating the crack length. So behind this specimen we have a camera so that we can see the crack lengths at the back of the specimen, because we need to make sure that the crack propagates equally on both sides. So that's why I check from this side, and from the other side I just check the camera. So this is what software gives me, some graphs and some numbers, but the most important figure for me here is the crack length now. But it's automatically done, so when the crack length reaches some certain point, it will just stop my test and then I will analyze the data. Together I have like over 80 specimens to test. That's why NTNU is helping us with some of the experiments, because it's unrealistic to finish all of these specimens within 4 years of my PhD. Yeah, I will be mostly using this machine, and at some point I will be doing the corrosion fatigue crack growth test, which means that my specimen will be placed in seawater, artificial seawater. So I have this tank here where I will make this seawater, and then it will be in the box for like 1 month, and also it will be growing the crack. Also, we are measuring residual stresses inside of these specimens, because, you know, like it's 3D printed technology. It doesn't look like it's been made with layers, but it's actually made with layers. And that's why lots of residual stresses, they are locked inside, and they will affect the behavior of our materials. So that's why we are doing all of these tests here and NTNU. And then we're also measuring the residual stresses in ILL, France. And here in Cranfield we have this lab with large machines. So all of the specimens I made myself in this lab.